Alright, so continuing on with the theme of inverse trig functions, let's see what else we can do with them. So, I want you to evaluate all of these compositions of trig and inverse trig functions. Pause the video, do that, and pause when you're ready to check your answers. Okay, so these are the answers. Hopefully you got them all right, but if you didn't, or even if you did, let's discuss a little bit. And as usual, by discussing, I mean I'm going to talk, and hopefully you're listening, but who knows. Anyway, so whenever we deal with any composition of functions, but specifically trig ones we care about, since that's what we're doing right now, but really it's true for any. You want to work from the inside out, and the first thing you need to look at is does the input to the inside exist within the domain of the function. So for instance, the arctangent of 36. The domain of the arctangent function is all real numbers, so 36 is a good input. I don't know what the output is, but I know that the tan of the arctan of 36 is going to be 36. You can prove that to yourself or demonstrate that to yourself by using values that you do know. So for instance, what if you did the tan of the arctan of 1? Well, I know the arctan of 1 is pi fourths, and the tan of pi fourths is 1, so it would be 1. The sine of the sine inverse of negative 0.3. Again, is negative 0.3 within the domain of the sine inverse function? Yes, it is, because it's between negative 1 and 1. So then the sine of the sine inverse of negative 0.3, I get negative 0.3. The cosine of the arc cosine of 36. Is 36 within the domain of the arc cosine function? No, it is not. So my answer, right there, I'm done. I can't do anything. Does not exist. Is 5 pi fourths within the domain of the sine function? Yes, it is. What is the sine of 5 pi fourths? The sine of 5 pi fourths is negative root 2 over 2. What is the sine inverse of negative root 2 over 2? It's negative pi fourths. Is pi thirds within the domain of the tangent function? Yes, it is. What is the tangent of pi thirds? The tangent of pi thirds is root 3. What is the tangent inverse of root 3? It's pi thirds. Is 7 pi fourths within the domain of the tangent function? Yes. What is the tangent of 7 pi fourths? It is negative 1. What is the arc cosine of negative 1? It is pi. So now looking at these, what do we notice? Or specifically, what do you notice? I notice a lot of things. So I want you to pause the video, and I want you to answer these questions. Under what conditions will the sine of the arcsine of x equal x, and the arcsine of the sine of y equal y? Under what conditions will the cosine of the arccosine of x equal x, and the arccosine of the cosine of y equal y? And under what conditions will the tangent of the arctangent of x equal x, and the arctangent of the tangent of y equal y? So pause the video and answer those. Okay, moving on. Let's do some graphs of some arc or inverse functions. Now, keep in mind, the inverse functions are not periodic functions, so we do not graph these like we do the regular sine, cosine, secant, cosecant, tangent, cotangent functions. We just kind of plot points. So in order to graph this, let's first actually graph y equals arcsine of x. Now remember, for inverse functions, when we draw our axis, the inputs are the ratios of sides of the triangles, and the outputs are the angles. So our axes kind of change. And now, like I said, just kind of plots of points. So what is the arcsine of 0? It's 0. What's the arcsine of 1? It's pi halves. What's the arcsine of negative 1? It's negative pi halves. Now, to understand the shape, I'm also going to put in negative 1/2 and 1/2, because I know that at negative pi 6, I'm at negative 1/2. So that's kind of like here. And at pi 6, I'm at 1/2. And what I'm trying to show is that pi 6 is a lot closer to 0 than it is to pi halves. So the curve is like this and like this. So that's the basic arcsine function. So what do I do if it's arcsine of 2x? Well, how does 2x transform the function? Now we need to think about our transformations of functions. So this is going to divide the x values by 2. So to graph that, I'm going to take this, I'm going to put it here, I'm going to take this, I'm going to put it here. So my y equals arcsine of 2x is going to be the graph in black. I'm not looking for a ton of accuracy on these. It's really just an understanding of the graphs and using your transformations. This one, I want you to try on your own. So try y equals arc cosine of x plus 2 and then minus 1. Again, I would recommend graphing the y equals arc cosine graph first. Pause the video, unpause when you're ready to check. Alright, so here, y equals arc cosine of x is going to look kind of like this. I know that when x is 1, cosine is 0. When x is 0, it's at pi halves, and when it's negative 1, it's at pi. So then I'm just taking this and I'm shifting it 2 to the left and 1 down. These points aren't going to be super great because here it's like pi minus 1, you know. But again, it's just the point of understanding the basic graph and then transforming it. Try y equals 2 arctan of x and then plus pi. Again, I would recommend graphing the arctan function by itself first. Pause the video, unpause when you're ready to check. Alright, so here I did them on 2 separate graphs. So here is just y equals arctan of x. It goes through 0, 0. There's a horizontal asymptote at pi halves, a horizontal asymptote at negative pi halves. If you wanted to, you could plot the point pi fourths, or I'm sorry, 1 pi fourths and negative 1 negative pi fourths. Those would be those points, and then it's this shape. So then if we are going to multiply the y values by 2 and then shift it up pi, it's going to look like this, where now there's going to be a horizontal asymptote at 0, a horizontal asymptote at 2 pi. This is now at pi halves and negative 3 pi halves. I'm sorry, pi halves and 3 pi halves, and then it goes through the point pi in the middle, but the shape stays the same. Okay, let's move on to the next example. I want you to evaluate the sine inverse of the cosine of 5 pi 6. Pause the video, unpause when you're ready to check. Okay, so here we get an answer of negative pi thirds. Here's the work on how I did that. First, cosine of 5 pi 6, negative root 3 over 2. Sine inverse of negative root 3 over 2 is negative pi thirds. Now try to evaluate the sine of the arc cosine of root 5 over 5. This is not a unit circle problem, so what do? We draw a, pause the video, and pause when you're ready to check. Okay, so here we end up with 2 root 5 over 5. How did I get that? Well, first, from arc cosine of root 5 over 5, I drew a triangle. The arc cosine, this is a positive input, therefore I know it has to be in the first quadrant. Cosine is also positive in the fourth quadrant, but because of the domain and range of the, or I should say specifically the range of the arc cosine function, this has to be in the first quadrant. That's how I knew it had to be in the first quadrant. So I know then that the adjacent side is root 5, the hypotenuse is 5, so then the opposite side is 2 root 5. Next one, try the cotangent of the arctangent of 5/8. Pause the video, unpause when you're ready to check. 8/5, very good. Now you could draw a triangle here, or if you were sneaky, maybe you recognize that, oh, these are reciprocals of each other. But if you didn't, that's okay, because you can draw a triangle, and that's a perfectly valid way to do the problem. Okay, here, write theta as a function of x. This is similar to a problem we did yesterday. Pause the video, and pause when you're ready to check. So our answer should be theta equals arctangent of x plus 1 over 10. And we get that again, so use the trig function that you're basically given, and what I mean by that is if I have the opposite and the adjacent, use tangent. So theta, tangent of theta is x plus 1 over 10, so then theta is arctan of x plus 1 over 10. Okay, so we want to make sure we understand how to evaluate trig functions, inverse trig functions, and the composition of trig functions and inverse trig functions. If it's on the unit circle, use the unit circle. If it's not, draw a triangle. And don't forget that the domain and the range are crucially important.